Hello, my name is Michal Przewozniczek from Wrocław University of Science and Technology, and I would like to present our work considering the multi-objective optimization with the multi-objective parameterless population pyramid. Now, let's start from some point of view on multi-objective optimization. Well, let's consider a B-objective problem for which we may have some Pareto front. What we can do with this problem? We can use the weight vectors, and actually using the weight vectors, we can make this B-objective problem to be a single objective, and we can optimize either only the first objective or only the second. Of course, we can produce many such weight vectors, and we can scale this B-objective problem to be a single objective in many different ways, with the use of many different vectors. So, what is the conclusion out of this? Well, we may say that the multi-objective problem is actually the set of single objective problems, and this set, of course, may be infinite. Well, so if we want to solve multi-objective problems effectively, then we should first solve the single objective problems effectively. Now, so the question is, which methods are effective in single objective optimization? So let's take a short view. Now, in discrete search spaces, the state-of-the-art EAs, for instance, are LT-GOMIA, P3, or FileOA. Now, the features of all these optimizers is that they employ linkage learning, so the problem decomposition techniques. They are all parameterless, and they decompose and use the decomposition information in various ways, and they are applicable to binary and non-binary search spaces. Now, for permutation-based problems, we have quite a similar situation. We have LT-GOMIA dedicated for permutation-based spaces problems, the P4 and, for instance, GMEDA and RKEDA. The features of all these optimizers are that they decompose the problem somehow. P4 and LT-GOMIA use linkage learning, GMEDA and RKEDA use the probabilistic model building. Many of these methods are parameterless, and they also decompose and utilize the information about the problem decomposition in various ways. Now, in continuous domains, we still have the similar situations. We have the RDG3, the CEC 2019 large-scale global optimization winner. We have CMAES, which uses in some ways the statistical analysis to decompose the fitness landscape. We have real-valued GOMIA with conditional linkages, which was the GECCO Best Paper nomination last year. And again, all these methods decompose the problem in some ways. Some may use linkage learning, some may use the other techniques. Many of them are parameterless, and again, they use the information about problem decomposition in various ways. So, to summarize, many state-of-the-art EAs employ linkage learning or other problem decomposition techniques. And you may get high research visibility with this kind of research, and many of these methods are published on the world top conferences, like the conference here, or in the world top journals. So, in problem decomposition in multi-objective and many-objective optimization, well, it's actually poorly represented. So it's a huge gap in the field, and linkage learning seems a reliable way of effectiveness improvement. So what stops us then? Why don't we use problem decomposition frequently in multi-objective optimization? Well, many objectives. If we have many objectives, then we may make many single objective problems. And the question is, which of these problems shall we decompose? Now, linkage discovery or other decomposition techniques may be expensive. So how often shall we update the decomposition information for so many single objective subproblems? Now, these are hard questions. So our proposition is to use multi-objective. We have proposed the multi-objective P3, which is based on the P3 method. And the linkage in P3 is generated on the base of many subpopulations, and this method maintains many different linkages, many different decompositions in the same time. We also employ weight vectors, and the intuition behind this proposition is that since P3 maintains many linkages, then maybe each Pareto front part will be covered by some of them, at least by some of them. So how it basically works. We have a pyramid-like population, like in P3, and for each level, which is each subpopulation, we maintain some problem decomposition information in the form of so-called linkage trees. And in each method iteration, we randomly choose a new individual. We choose randomly the weight vectors to make the multi-objective problem a single objective one. We optimize the genotype of the individual with the greedy optimization algorithm, and we introduce this new individual into the first level of the pyramid. And then we optimize the single objective problem with the use of the weight vectors and try to mix this new individual with the other individuals which already are a part of the pyramid. And if this operation is successful, then we add the updated, the improved individual on the higher pyramid level. So the main competing method is multi-objective GOMIA, which is a recent proposition which also uses statistical linkage learning and problem decomposition in multi-objective optimization. And here we have some results. For the practical problem, which is the scheduling problem, we compare with MOP3 is a red line, the black line is multi-objective GOMIA, and we compare them also with MOAD and NSGA2. We use the inverse generational distance, so we want to minimize the value of the measure. And you may see that with the increase of the problem size, the linkage learning methods significantly outperform the traditional ways of multi-objective optimization. Here we have the similar situation for the MaxCut problem, and we also have the multi-objective knapsack, for which actually the multi-objective GOMIA is the best one, is the best choice. And here we have some typical benchmarks for multi-objective optimization, for which the linkage learning methods also perform significantly better than MOAD and NSGA2. So to conclude, multi-objective P3 is competitive to state-of-the-art multi-objective dedicated GAs. The problem decomposition actually may significantly influence the field of multi-objective optimization, and our main future work directions are, well, we shall answer the main questions. So how precise shall we decompose? For how many single objective problems shall we get the decomposition information? And how to limit the costs of decomposition? Thank you very much for your attention.